Other preparation. This is the general tab. Let me open a file. In this general tab, you can put in the run title. You will also define the unit system. By default, it's a metric unit system. You could change it to English. And you can change the headings only. For example, this is kPa, degrees C. Click on change headings. This would change the PSI, degrees F. The values are not changed unless you use this option to convert values. For example, if I change it back to metric and I say convert values, then this message comes up. Observed values must be converted. Then this is converted to PSI. So this convert values will change the values by the appropriate conversion factors. So if I went back to convert values back, you go back to 100 in kPa. Relative tolerances. This identifies the accuracy to which the equations must be solved. For every segment, the mass balances are created for each component. Basically, input minus output must be equal to 0. Numerically, we cannot get it exactly equal to 0, so we must say that it must be within a tolerance. Here, the tolerance is defined as relative to the mass of the component in the segment. So, a relative tolerance of 0.001 means a tolerance of 0.001 times the mass of the component in that segment. It's recommended to use the default tolerance. If, however, you find that there's significant material balance error, you can add additional zeros, reducing the tolerance to make it a better solution. Similarly, for the energy tolerance. For the phase tolerance, this is based on the equation that the sum of the saturations in a segment must be 1. So in the three-phase case, oil plus water plus gas minus 1 is equal to 0. And in the actual life, it must be less than the phase tolerance, in this case 0.01. Well operating scenario. The user must choose one of the 4 options. The steam circulation scenario. In this case, all the steam injected will be produced back at the offtake point. There will be no perforation of the liner. The user will specify the steam injection pressure, quality and rate, and the reservoir temperature. The program will calculate the heat loss to the overburden and the reservoir and report back the pressure, temperature, rate profiles, and steam quality in the pipe segments. It's also possible to account for a small amount of leak-off. For the steam injection well scenario, in this case, we'll inject steam into the well and all the steam injected would flow into the reservoir. At the segments where the liner is perforated, the reservoir pressure must be entered and the amount of steam entering into each segment into the reservoir depends on the reservoir permeability, the skin, the pressure difference between the liner segment and the reservoir segment. In the production well scenario, using a fixed reservoir input rate, we have to enter the reservoir oil, water, and gas rates by segment. You can have a fixed flat profile or a varying profile. It can be of any shape. Some segments may not even have any production rates at all. the rates entered are fixed. They're independent of the reservoir pressure and the liner segment pressures. So for a given offtake pressure, the program will calculate the pressure and rate profiles along the pipes such that all the specified input rate would flow out of the well at the surface offtake point. The next scenario is the production well with variable reservoir influx, and in this case here, the reservoir input rate is a function of the entered reservoir pressure, temperature, fluid saturations, that is, the fluid mobility. The offtake pressures and reservoir pressures will be fixed, and the program will calculate the production rate and pressure profile in the pipes. Maximum number of iteration cycles. The solution to the set of Wellbore mass and energy balance is performed in a number of iteration cycles. At the beginning of each cycle of iterations, a Wellbore gradient is established, and Newton iterations are performed to obtain convergence. Then the Wellbore gradient is recalculated, and the gradient change is found. The gradient change will be tested against the gradient change target. The default change target is 0.1. The iteration cycle is repeated until the gradient change is reduced to the gradient change target. The default maximum number of cycles is 300. The user should increase the number of cycles if the program reports a reduction in gradient change but fails to meet the target after the specified number of iteration cycles. The larger the number of segments, the more the number of iteration cycles is necessary. Maximum number of Newton iterations. A large number may be needed to get convergence. If the number of Wellbore segments increases, then more iterations may be needed. This is the gradient change target, so the program will converge when the Wellbore gradient in the pipes in the last iteration cycle is less than this value. Sometimes this target may be too hard to achieve, even though a good solution has been obtained with, say, 0.2 or 0.5. You may increase this value and then see if the answers are reasonable with good material balance. Convergence parameters. These are parameters used to modify the equations in order to get convergence. They entered from a min to max range with a number of steps. The program will try varying in steps each of these parameters in the grid search until it finds one combination of parameters that converges to a solution. If you find difficulty in getting convergence, you may try to increase the range of these numbers. This is the maximum number of allowed change per Newton iteration, just to prevent overshooting each Newton iteration.